So in the previous lecture we looked at the cubic well, and we noticed that the cubic well is a three-dimensional well and the energies are quantized and they are defined by three quantum numbers instead of one. Those quantum numbers are nx, ny and nz, and the energies are given by characterized by nx, ny and nz, and they're given by h bar squared pi squared over 2ml squared So this is something that we derived in the previous lecture. These are whole numbers starting from 1, each one of them, and they are independent. Alright. Is the energy quantized? Yes, it is. Is the momentum quantized? Yes. The x component of the momentum is quantized, the y component is quantized, and the z component is quantized. And that is because kx is quantized, and kx depends upon nx. Ky is quantized, and kz is quantized. So the quantum number nx defines the quantization of the x component of the linear momentum, ny defines the quantization of the y component of the linear momentum, and z defines the quantization of the z component of the linear momentum. Corresponding to a quantum number, some property, some variable is quantized. So this is a quantum number, it quantizes a momentum. A quantum number, it quantizes a momentum, and these are all linear momentums, because we're looking at a 3D cubic well. And then we also looked at the concept of degeneracy. So if I make a table, I started making a table in the previous lecture, I'll do it again, and I have the energies here and the wave functions. The wave functions are also dependent on nx, ny and nz, and the wave functions represent standing waves, and these are wave functions of the particle of the electron that is trapped inside the well. You see, what physically, if you have a semiconducting material and you have a defect inside that material and the electron is trapped at the defect, it can be pictured as a 3D cubic well. So cubic wells are extremely important. Now if we look at the smallest energy, now we're talking about energy in units of h bar squared pi squared over 2ml squared. So the smallest value of the energy is of course 3 times this factor. So here what I'm writing in fact is the energy divided by h pi squared 2ml squared. This is what I'm writing in this column, and I can write the wave function as well. Some constant c sine of pi x over L, sine of pi y over L, sine of pi z over L. So one set of values of the quantum numbers, one wave function, one energy. But then if I make this 2, one of these I can make 2, and they will correspond to different states, they will correspond to different wave functions, but each one of these will have the same energy. So this will have 6 times the energy. And the wave function corresponding to this set of quantum numbers is some c sine of 2 pi x over L, sine of pi y over L, sine of pi z over L. And you can write the wave functions corresponding to this set of quantum numbers, to this set of quantum numbers. Now there are three different wave functions and three different probability distributions, because the probability distributions are in fact modulus squared of the wave function. So three different probability distributions, three different wave functions corresponding to the same energy. Hence, if I draw an energy level diagram, this is the lowest energy corresponding to the state 1, 1, 1. That is, Nx is 1, Ny is 1, Nz is 1. Corresponding to the next energy, I have three different states. I have 2, 1, 1, I have 1, 2, 1, I have 1, 1, 2. Now all three of these wave functions, they are different wave functions, different states, different probability distributions, but all three of them have the same energy. So if this diagram represents energy on the vertical axis, then these three states, these three wave functions, अब देखो मैंने wave functions के लिए states का लफ्ज़ भी इस्तेमाल करना शुरू कर दिया, ये तीनों states एक ही energy पर हैं. So this is a threefold, this is called threefold degeneracy. Degeneracy means different wave functions but the same energy. Now if I go to the next level, which is 311 or 221, I can make this 2 2 1 2 1 2 1 2 2. This will give me 4 plus 4 8 9 here. Now again there are three different states with the same energy. For example, if I write the wave function for this state, I would get C sine of 2 pi x over L sine of 2 pi y over L sine of pi z over L. Whereas the wave function for this particular combination of quantum numbers is C sine of 2 pi x over L sine of pi y over L sine of 2 pi z over L. So I can draw three wave functions here. This difference, this is 3 6 9. Three different states, but all of them with the same energy. And what's the next energy level? What should I write here? 311. Not 222. 311. Because that has a low energy. 311 is 9 plus 1 plus 1. 11, 222 is 4. Okay, so we write 3, 1, 1, 1, 3, 1, 1, 1, 3. Again, this gives me 11 times the energy. This is threefold degenerate again. But now this spacing is 2 units of energy. There are 9, 6, 3, this is 11. So the energy levels are not equally spaced in this cubic well. So I have 3, 1, 1, 1, 3, 1 and 1, 1, 3. And then I have 2, 2, 2, 12. And this is one fold degenerate. There's only one state that has this wave function. So I will just have one state here. 2. Now just to complete this table, or this table goes on forever. You can have as many excited states as you like. This is the ground state. This is the first excited state comprises 3 states. The second excited state comprises 3 states. And you can make transitions between these states. If an electron is excited to this state, it can jump from the excited state back to the ground state and emit a photon. Or you can absorb a photon and have transitions between states. And you can find the frequency of the emitted photon or the absorbed photon and the wavelengths. So if I go ahead in this table, what's the next state that I can write? One, two, three, right? 4 plus 9, 30. 1, 2, 3. I can write 1, 2, 3. I can also write 1, 3, 2. I could also write 2, 3, 1. I could write 2, 1, 3. I could write 3, 1, 2, 3, 2, 1. So these are now 6 states, all with the same energy, and the energy is 1 plus 4 plus 9, thus 14 units. Now I have 6-fold degeneracy in the cubic well. With 3 quantum numbers, the maximum degeneracy that I can have is 6. Because all 3 quantum numbers are now distinct, they are different. So, using the rules of probability, I can now have 6, maximum 6-fold degeneracy with a cubic well. And they have different wave functions. For example, the wave function corresponding to this combination of quantum numbers is some constant of proportionality, normalization constant C, sine of 3 pi x over L, sine of pi y over L, sine of 2 pi z over L. Now I have a 6-fold degenerate state, and I should be able to plot 6 levels here. 1, 2, 3, 4, 5, 6. So I can build up and construct an energy level diagram. But the question is, where is this degeneracy coming from? Now, as a homework, before our next class, I would like you to look at the following. Suppose instead of a cubic well which has an electron bound inside a cube, and all 3 sides of the cube by definition are equal. What if I don't have a cube but a parallelepiped, or 2 sides are equal and it's a cuboid? 2 sides are equal but the third side is distinct. Will the degeneracy be higher or lower? So this is a problem that I would like you to address and solve for yourself. That is, if 2 sides are equal and the third is unequal, will I get the same table of the shape? Just take 2 sides to be L1 equals L2, which is not the same as L3. Just take a cuboid and construct standing waves inside the cuboid using exactly the same procedure, and see if you get the same level of degeneracy. You will notice that if the symmetry collapses, if the symmetry of the problem collapses, the degeneracy is lifted. That is, there is less degeneracy. Degeneracy is linked with symmetry. So there is an intimate relationship between degeneracy and symmetry. And this is something you have to explore on your own. Now we have a large number of wave functions corresponding to the energy levels. What is the meaning of these wave functions? In order to grasp the meaning of the wave functions, we have to take the probability density, which is the modulus squared of the wave function. So this is a three-dimensional wave now. It's a three-dimensional matter wave. Now I have a simulation that shows what these waves look like. So bear with me for a couple of minutes while I pull that up, and then I'll show it to you.
सर degeneracy आपने कहा था कि अगर सेम एनर्जी लेवल पे डिफरेंट वेव फंक्शंस हो तो जो 2 लेवल है आपने कहा था वन फुल degeneracy उस पे तो यही है।
हाँ, एक ही लेवल है, कोई डिजेनरेसी नहीं है। ये वहां से ऑन करना मल्टीमीडिया, उधर से उधर स्विच है उधर। And then we'll start looking at what is meant by orbitals. So do attempt this cuboid kind of potential well. It's not cubic, it's a cuboid. Two lengths are the same, one is different, and see if you get the same degeneracy or if you get smaller level of degeneracy. Now in this particular simulation, since it's difficult to show 3 dimensions, we have a 2-dimensional well. 2-dimensional well means an electron in a 3-dimensional well, an electron is trapped in a volume, such as in a solid. In a 2-dimensional well, the electron is trapped in a sheet. It moves in a flat land. एक शीट के अंदर मूव करता है, शीट से बाहर नहीं आ सकता. इस तरह एक चूंटी है, वो जमीन पर चलती है, वो छलांग नहीं मार सकती. ठीक है, तो वो एक 2-dimensional दुनिया में रहती है चूंटी. ठीक है, तो if an electron lives in is like an ant and lives in a 2-dimensional world, in a sheet or in a film, then if the well is 2-dimensional, this is what the simulation is showing us, and results are the same. So in 2 dimensions, how many quantum numbers would we have? 2, nx and ny, and both of them are distinct, independent. They can be integers ranging from 1 up to infinity. Now in this particular simulation, which is in Mathematica, and this pointer doesn't work. Good point. अच्छा, okay, ठीक है. ये देखिए, ये सिमुलेशन है, मैथमेटिका में लिखी गई. अब एक है वेव फंक्शन, एक है वेव फंक्शन का मॉड्यूलस स्क्वायर्ड. वेव फंक्शन का मॉड्यूलस स्क्वायर क्या होता है? Probability density. So we were plotting the probability density, or we plotting where the electron is most probable to exist. That is what the wave function tells us. That is what the field, it's a field. Before you measure the field, it's everywhere in space, and when you make a measurement, it collapses to a point. So this is what the situation looks like before you take a measurement. That is, you have a cloud or an electron is spread out in space, and you make a measurement, you collapse. You make multiple measurements, this tells you the frequency or the number of times where you'll be able to find the electron. So for nx equals 1 and ny equals 1, this is the x dimension and this is the y dimension. This is y, this is x. And x, the trap is from 0 to L in the x direction and from 0 to L in the y direction. For the ground state, nx is 1 and ny is 1. So the fundamental or the ground state standing wave is sine pi x over L, sine pi y over L. You take the modulus square, you get sine square pi x over L, sine square pi y over L. Now you have to plot it. So you vary the value of x, you vary the value of y, and you get an antinode in the middle. You're familiar with one-dimensional standing waves. That is what, you know what a one-dimensional standing wave is. The fundamental has nodes at the walls and a hump in the middle. In 2 dimensions, there will be hump in the center of the 2-dimensional plane, right? So this is the probability density of the ground state.
सेंटर पे मैक्सिमम है प्रॉब्लम.
सेंटर पर मैक्सिमम है. देखो बड़ी अजीब बात है क्वांटम मैकेनिक्स में, सेंटर पर मैक्सिमम है. ठीक, क्लासिकली आप कहते हैं क्लासिकली. अच्छा, अब आपने क्लासिकली देखते हैं. ये तो देखो, इसको कहते हैं एक किस्म का सरफेस प्लॉट, कि ये एक्स डायमेंशन है, ये वाई डायमेंशन है, और एक सरफेस प्लॉट है. ठीक है, मैटलैब में आप ये कर सकते हैं, ये खुद से, इतनी आपके पास हुनर है, आपके पास कर सकते हैं आसानी से प्लॉट इसको. अगर इस तरह के प्लॉट को कहते हैं काउंटूर प्लॉट. जिस तरह जमीन का एक काउंटूर प्लॉट होता है, वैल्यूएशन बताता है. ठीक है, मरी 3000 मीटर पे है, लाहौर 0 मीटर पे है. ठीक है, वो एक आपको काउंटूर प्लॉट दे सकते हैं ना आप, रिलीफ प्लॉट. तो ये काउंटूर प्लॉट है. आप सेंटर में देखेंगे इट्स वाइट, सो दिस द ब्राइटर रीजन्स कॉरस्पॉन्ड टू लार्जर probability density. So this is a contour plot, this is a surface plot. Now let's move to the next level, which is, let's advance nx by 1. All right, so now nx is 1. Now the wave function nx is 2 and y is still 1. The wave function has now changed. It's now sine 2 pi x over L, sine pi y over L. So the spatial frequency, the k along the x dimension has changed. So now there should be 2 antinodes along the x direction. But along the y direction, along this direction, there is still 1 antinode. So now you have 2 humps as you move along the x direction. You start here in a valley, you climb a mountain, you come down, you go back into a valley, climb a mountain, and come back. But if you move in the y direction, you just climb one mountain. So this is the wave function corresponding to the first excited state, but it must be twofold degenerate. The other state which has the same energy is when nx equals 1 and ny equals 2. Right. So this is the degenerate state. The first excited state has a degeneracy of 2 in 2 dimensions. 3 dimensions में तो degeneracy 3 थी ना, 2 dimensions में 2 होगी. तो अब 2 dimensions में तो जो degenerate state है nx 1 है, ny 2 है. ठीक है, तो अब y dimension में 2 humps हैं. So this is the probability density. There are 2 points where the probability of finding the electron is maximum, not one. There is a hump here and a hump here. ठीक है, इसी तरह we can advance the values of nx and ny. So this is what happens when we advance nx to 3 and ny remains 2. You get 3 humps in the x direction and 2 humps in the y direction. Okay, and you can play this out. You can different wave functions. Okay, let's stop this at some value of say 5 here and 4 here. This is your probability density diagram now. Nx is 5 and y is 4. You look at the probability distribution function. You have 5 humps in the x direction and 4 humps in the y direction. And you know what the wave function is. Sine 5 pi x over L, sine 4 pi y over L. Again, remember this is not a rectangle, it's a square. So now there are regions in space. There are regions in space where there is very small probability of finding the electron. And there are regions in space where there is a very high likelihood of finding the electron. This one electron, याद रखो, मैं वेव फंक्शन की बात अब दोबारा आपको समझाने लगा हूँ कि इलेक्ट्रॉन तो एक ही है, ठीक है. Before you make a measurement, this is the picture of the electron. It's spread out, it's smeared in space because you haven't made a measurement. It's a field. This is the field of the electron, or the wave function, or the modulus squared of the wave function, in fact. But we can plot the field of the electron as well. But when you make a measurement, you make it a measurement once, you'll find the electron somewhere. It can be somewhere on this grid, somewhere here. But when you prepare an identical system, which is one electron system, and you make another measurement, and then you prepare an identical system, you make a large number of measurements and plot the frequencies of occurrences of where the electron exists, and you do it a large number of times. This is the kind of plot that you will get. That is, the electron in most cases will exist in these bright regions. But remember, this is the wave function, the probability density of a single electron. Now the question is, if the wave function is 0 in between the humps, the probability density is 0 at certain points, you can find out the nodes in a standing wave. How does an electron get across the nodes? Tunneling? How does an electron get across the nodes? ये देखो, बड़ा इंपॉर्टेंट क्वेश्चन है, इसको याद रखो. अगर क्वांटम मैकेनिक्स के इस कोर्स में कोई चीज़ याद रखने वाली एक चीज़ है ना, वो ये है, बाकी भूल जाना आज से 10 साल बाद. देखो वो चीज़ ये है कि देखो कुछ रीजन जो बिल्कुल ब्लैक रीजन है ना, यहाँ पे वहाँ पे प्रोबेबिलिटी डेंसिटी 0 है. स्टैंडिंग वेव में बाज़ जगहों पे वेव फंक्शन 0 हो जाता है ना, जहाँ नोड होता है, तो वहाँ प्रोबेबिलिटी डेंसिटी भी 0 हो जाएगा. तो एक तरफ हाई प्रोबेबिलिटी रीजन है, फिर 0 प्रोबेबिलिटी, फिर हाई प्रोबेबिलिटी. So how does the electron get from a high probability region to a low probability, to another high probability? It must cross the node, and if it crosses the node, then there must be some experiment which tells us that the electron exists at the node. But this wave function is telling us that the electron cannot exist at the node. So how does an electron get across the node? It's not tunneling.
It acts as a wave when going from one node.
It acts as a wave when going from one node to the other. किसी को इसका जवाब पता है? देखो हमने वन डायमेंशनल वेल में भी हमने स्टैंडिंग वेव बनाई थी ना, 0 स्टैंडिंग वेव्स की एम्पलीट्यूड 0 भी था. क्या है इसका जवाब? सवाल समझ आया? तो सवाल का जवाब क्या है? नहीं. देखो एक ग्रीक फिलोसोफर था ज़ीनो कहता था कि एक अगर आप तीर फेंके, ठीक है, अब आप तीर फेंके पॉइंट ए से पॉइंट बी तक, अब दी एरो इज कॉन्स्टेंटली मूविंग, बट इफ यू टेक पिक्चर्स ऑफ द एरो, each picture shows that the arrow is at rest. The next picture also shows that the arrow is at rest. And if you take a large number of pictures, an infinitely large number of pictures, in each picture the arrow will be at rest. If the arrow is always at rest, then how can the arrow move at all? This is called the Zeno's paradox. Now this is the Zeno's paradox. Zeno asked the wrong question. Similarly, I am asking the wrong question here. जो मैं आपसे सवाल पूछ रहा हूँ, quantum mechanics only allows us to ask certain questions. This is a wrong question quantum mechanically. When we talk about quantum mechanics, now I would like to hear to what you were trying to say.
Sir, how do we know that there is not another entity associated with an electron that fills the p-space?
These are called hidden variables, and there are experiments, a large number of experiments that disprove that hidden variables exist. So hidden variables don't exist, we know that. So the answer to this question is stop thinking of the electron as an object in motion.
Is it true that the electron doesn't have to cross the node itself? It just exists in one of these nodes, and that.
You similar. You are very close. Dekho, stop thinking of the electron as an object in motion. Stop thinking in. Take out Bohr's mind from your mind and put in Schrödinger's mind in your mind. That's the way to answer this. Stop thinking of the electron as an object in motion. The electron is everywhere. Or the electron is completely defined by the wave function. The wave function is the field of the electron. The field of the electron can exist at some points and the field can be zero at some points. Which means that the probability density can be finite at some points and zero at some points. So this is a picture of the electron at one instant before you see the picture, before you make a measurement. This is where the electron really is. This is where the electron can potentially exist. Stop thinking of an electron that in some cases it has to go from here to here. The electron is everywhere. One electron is not a particle, it's a field. It exists everywhere and it's not a particle in motion. Because if it's a particle in motion, then it has to go from point A to point B to C to D to E and then you make a measurement. Sometimes you measure it to be here, sometimes here, but that's not the proper way of thinking about it. Think of the electron, one electron, it exists everywhere and it's defined by this wave function.
So does that mean that the field is discontinuous? That field?
No, the wave function is always continuous. The field is always continuous. It goes like a sine wave is always continuous. वो zero भी रखता है लेकिन sine wave में continuous तो है. वो तो property है wave function की जी.
So then why do we associate kinetic energy to an electron? And if suppose we bring another particle in that cube, would the two interfere?
Yes. Second question answer first. Two particles in this well, there are two waves, there are two fields, okay? And they will interfere. Even one electron will interfere with itself. That's the first lecture. So two particles inside, they will have their own waves and waves will constructively or destructively interfere. Yes. Second question, why do we associate a kinetic energy if the electron is not in motion? Because ultimately when we are measuring the electron, we are detecting it as a particle and it has a certain energy. And we associate kinetic and potential energies with energies. So we can measure the momentum. When it has momentum, it has kinetic energy as well. But before you make a measurement, the electron is just a field. It's not an electron, it's not a particle in motion.
How can the field vary so rapidly in a continuous region?
Why not? Because we are increasing the quantity. This is an excited state. When you have an excited state, the value of K is so small that you have a large number of ripples. If I increase the value of Nx or Ny even further, see the way, remember we're talking about time independent. This is not with time, this is with space. In space the wave function changes rapidly. That's what the solution of the Schrödinger equation tells us.
If we conduct an experiment and observe that the electron is present in one of those areas, one of the bright areas, and then if we stop observing the experiment, will the wave function spread to the whole area again, or will it be confined to that bright area only?
No, that's a very good question. When you have a field or a wave function, you collapse the wave function. Suppose you measure the electron exists here. Now you stop the measurement. The electron does it come back to its original state or not? No, it doesn't. On its own, it doesn't. When you are making a measurement, you are collapsing the wave function to some new wave function. And whether it comes back to its original wave function to an excited state, it needs to get some energy to do it. Suppose you are collapsing it to a ground state or to one of the levels, it does not automatically go back to the original state.
So this we are right now seeing the conditioned wave function for an electron. So can we generalize this to every particle?
Yes, this could be an electron, this could be any particle. This could be a proton, this could be a bacterium, this could be virus, this could be a buckyball, this could be a muon, a pion, any particle. You just have to write the proper potential energy function. More questions? अब आपसे नहीं कोई और सवाल पूछे.
Intriguing. Thing that is intriguing me a lot. So if I've asked this question to the GA before as well, but I still didn't get a proper answer. So if what is intriguing is the fact that
Don't say you didn't get a proper answer. You weren't satisfied with it, or
yeah, that's right. So if I close my eyes, everything around me is waves. So why don't the probabilities change if we're following the uncertainty principle as well?
you see, we're talking about time-independent problems here. If the potential energy function changes with time, yes, the probabilities will also change with time, because there's a time-dependent part in the wave function as well. Yes, the probabilities do change with time. But if the Hamiltonian or if the potential energy does not change, the wave function remains the same. It only acquires a phase factor, or the probability density doesn't change. Alright, so if you close your eyes, everything is really a wave. Okay, it's a field. But what we are observing are photons, are particles that are being reflected from your bodies, from the floor, from the ceiling. We're detecting, when we make a measurement, we are collapsing the wave function. There's no longer a field. थोड़ा सा आगे चलें. हाँ, आप पूछें. How can it have a mass? You see, look at gravity. Gravitational field है ना. You have an object. ये ball points please ना करें. You have an object of a certain mass. It produces a field, but there's mass that is producing the field. You have a charge, a positive charge. It's a charge. It's producing an electric field. Here you have a wave, and we know that associated with the wave is there is a momentum. That's the de Broglie relationship. There's a momentum. There must be a mass, and there's a wavelength. That's the wave-particle duality. That's what de Broglie told us, that there's a momentum, there's a wavelength associated with it. ठीक. अच्छा, एक बात मैं अब आपसे पूछता हूँ. वो बात ये है कि देखो, ये तो क्वांटम पिक्चर है ना. क्वांटम पिक्चर तो बड़ी अजीब पिक्चर है भाई, कि भाई बाज़ जगहों पे आप इलेक्ट्रॉन को फाइंड कर सकते हैं, बाज़ जगहों पर नहीं कर सकते. What is the classical prediction? If you have a particle in an infinite wall, in an infinite well, particle in an infinite well, what do you predict classically? What about the probabilities? Will you have the same probability of finding the electron everywhere, or will you have this modulation effect, that is the particle may exist somewhere and it may not exist? You suppose you have a squash court, ठीक है, इसकी दो दीवारें हैं स्क्वाश कोर्ट की, और बिल्कुल फ्रिक्शनलेस दीवारें हैं, कोई फ्रिक्शन नहीं है कहीं पे. अब एक माहिर खिलाड़ी आके एक जोर से स्क्वाश का रैकेट चलाता है और गेंद एक दीवार की तरफ फेंकता है. देयर इज नो फ्रिक्शन, ठीक है, देयर इज नो लॉस इन द स्पीड ऑफ द स्क्वाश बॉल. अब वो मूव करेगा ना मुसलसल बिटवीन द वॉल्स. It cannot go outside the walls because these are infinitely high walls. So what about the probability of finding the tennis ball? It should be the same everywhere. But that's not what we find in this quantum picture. That's not what we find in this quantum picture. But suppose if I keep on increasing the values of n. If I keep on increasing the values of n, what do we get? In fact, 7 is the maximum number that I can get in this simulation. This is the maximum I can get in this simulation, but there is a large number of antinodes. There is a large number of humps in this. If n goes to 100 or 1000, then
becomes sort of constant.
The probability density becomes more or less constant. Because the variation is so rapid. The variation is so rapid that on average you find a constant probability. So the classical world is the quantum world in the limit of very large quantum numbers. Okay, बड़ा important statement है. The classical world, मैंने शुरू वाले दिन lecture में कहा था कि जो classical world है वो non quantum नहीं है, वो average quantum है. The classical world is obtained when you go to very large quantum numbers. So this is something that I had to tell you about degeneracy and a physical picture of what happens when a particle is trapped inside a potential. But the ultimate goal that I would like you to learn from one of the goals is that we understand the hydrogen atom. अब हाइड्रोजन एटम देखो, इतना सिंपल एटम है, एक इलेक्ट्रॉन है, एक प्रोटॉन है, लेकिन किताबों की किताबें लिखी गई हैं हाइड्रोजन एटम की समझ नहीं आती. It's so complicated. In the course on which we call atomic and laser physics, which third year physics students study, they go to a next level of complication in the hydrogen atom. In metric FSC A levels, we studied about quantum numbers in the hydrogen atom. It's a very simplistic picture. Now in this course will be useful to you if we understand where those quantum numbers are coming from and what is the physical meaning of those orbitals. If we repeat the same material, then there's no use studying physics. Now we have to make a connection with what are orbitals, how do electrons behave inside atoms, which are real objects. These objects, one-dimensional well, two-dimensional well, three-dimensional well, they have a lot of applications, but they're slightly removed from reality. ठीक है? तो अब हमें बात करनी पड़ेगी हाइड्रोजन एटम की, और हम फ्राइडे को भी उसकी बात करेंगे, लेकिन मैं आप थोड़ी सी मोटिवेशन बनाना चाह रहा हूं हाइड्रोजन एटम के मुतालिक. ठीक है? तो लेट्स गो बैक टू द ब्लैक बोर्ड. Turn this off. First of all, a quick review of spherical coordinates. Everyone knows what spherical coordinates are? सबको पता है? एक दफा रिव्यू कर लूं? हाँ बिल्कुल. आप लोग नहीं में जवाब नहीं देते, हाँ में जवाब देते हैं. अब देखें, कार्टेशियन कोऑर्डिनेट से तो बचपन से हम वाकिफ हैं. ये देखें, ये थ्री डायमेंशनल कार्टेशियन स्पेस है. इस पे कोई पॉइंट ले लें, उसके कोऑर्डिनेट्स होंगे एक्स, वाई और जी. कोई शक नहीं. लेकिन स्फेरिकल कोऑर्डिनेट सिस्टम हमारी कोई खास मोहब्बत नहीं है एक्स, वाई और जी के साथ. ये एक फ्रेम ऑफ रेफरेंस है. कोई और फ्रेम ऑफ रेफरेंस भी हम इस्तेमाल कर सकते हैं अपनी कन्वीनियंस के लिए. तो हम स्फेरिकल कोऑर्डिनेट सिस्टम यूज करेंगे हाइड्रोजन एटम के लिए. तो स्फेरिकल कोऑर्डिनेट सिस्टम में जो वेरिएबल्स इस्तेमाल होते हैं वो है आर, थीटा और फाई. इस पॉइंट को एक्स, वाई, जी के साथ साथ हम आर, थीटा, फाई में भी रिप्रेजेंट कर सकते हैं. एंड हाउ डू वी डिफाइन? R is simply the distance from the origin. This is R. And theta is the angle of declination from the z axis. कि अगर आप एक रे बनाएं इस पॉइंट P और origin के दरमियान, तो look at the declination from the z axis. कितना ऊपर से नीचे आना पड़ेगा. ठीक है? थीटा. इसको एंगल ऑफ को लैटिट्यूड भी कहते हैं. लैटिट्यूड नॉर्थ पोल 0 डिग्रीज पर है, इक्वेटर कितने पे है? 90 डिग्रीज पर. साउथ पोल 180 डिग्रीज पर, पाकिस्तान 35 डिग्रीज पर, 63 डिग्रीज पर सॉरी. तो ये एंगल ऑफ को लैटिट्यूड है थीटा. और फाई क्या है? यू ड्रॉ प्रोजेक्टर ऑन टू द एक्स वाई प्लेन एंड देन यू ड्रॉ a ray from O to the point of the projection. This angle from the x-axis is called the phi, the azimuthal angle. ठीक है? ये azimuthal angle है या longitude की तरह की चीज है, और ये co-latitude angle है. मैथमेटिशियंस हो सकता है इस फाई को वाई से जाहिर करें, लेकिन आपने इसी कन्वेंशन को फॉलो किया, तो पढ़ा भी है कि नहीं? ठीक है, तो you can always go between spherical coordinates and Cartesian coordinates. X equals r sin theta cosine phi, y equals r sin theta sin phi, and z equals r cosine theta. So this is how, if you know x, y and z, you can find what the theta, phi and r should be. For example, r should be x square plus y square plus z square under root and so on. Theta has to be tan inverse x square plus y square over under root over z and so on. So you can interconvert between the two frames of reference. Alright, sometimes it's easier to use the cubic the Cartesian frame of reference. For example, in the three-dimensional well, there is no point in using the spherical coordinate system. In the hydrogen atom, there is no point in using the Cartesian coordinate system, because it's going to make your lives miserable. So complicated. अच्छा, एक और चीज जो मैं आपको बताना चाह रहा हूँ, which is extremely useful when you look at probability densities, because probability density is probability per unit volume. So volume is very important in the spherical coordinate system. Suppose I draw an object, a small object, three-dimensional object. I want to find the volume of this object, dV. In spherical coordinate system, you know what the volume would be? In the Cartesian coordinate system, the volume is simply dx, dy, dz. But in the spherical coordinate system, it's not dr, d theta, d phi. It's ludicrous writing something like this. This is not the volume element. The volume element, in mechanics you must have studied, in electromagnetics you must have studied problems of this kind. नहीं? No? Calculus में पढ़ा है ना? तो क्या होगा volume element? चलो मैं आपसे पूछता हूँ कि ये जो length है ये क्या है? If this angle is d theta, what is this length? r d theta. And what is this length? This is dr. How much you go forward in r? This is dr. And we have to find out what this length is. So you make a projection here. You have to find what this arc length is. And what is this arc length? r sin theta d phi. So this is r sin theta d phi. So now we have the three arc lengths that make up this small volume. So the volume of this element dV is r square sin theta dr d theta d phi. So this is the volume of a small element when we talk about a spherical coordinate system. I can see empty and blank faces, which means that you're not very comfortable with it, but I would assume that this is something that you should know, or at least go home and understand this expression. That is, you just take this small object, look at the different arc lengths, look at the length of this arc, and when dr is small, d theta is small, an arc is just a line segment, it's a straight line. And this is the volume of this small element. Right, now let's look at the Schrödinger equation. First of all, when we deal with the Schrödinger equation, we have to deal with the potential energy function. बात सुने गौर से. जब भी हम श्रोडिंगर इक्वेशन सॉल्व करने की जुस्तजू करते हैं, निकलते हैं, ठीक है, तो पहला स्टेप क्या होता है, पोटेंशियल एनर्जी फंक्शन क्या है वो पता होगा तो कुछ करोगे ना. जीरो है, फाइनाइट है, कर्व्ड है, स्लोप्ड है, पोटेंशियल एनर्जी फंक्शन क्या है. तो हाइड्रोजन एटम में एक इलेक्ट्रॉन है, वो किसी पोटेंशियल फील्ड में है, उसके लिए पोटेंशियल एनर्जी का फंक्शन क्या होगा. व्हाट्स द पोटेंशियल एनर्जी फंक्शन फॉर एन इलेक्ट्रॉन इनसाइड अ हाइड्रोजन एटम. Is it a cubic well, an infinite well? What's the potential energy of an electron? Inside a hydrogen atom. I give you 2 minutes to think about it. And if you can write it down on your papers, I'll be very grateful. इस मर्जी में दे दो. माइनस पी.
Spherical infinite well.
Spherical infinite नेगेटिव इन्फिनिट है कि न्यूक्लियस पे नेगेटिवली इन्फिनिट जाता है. हाँ, it's like a spherical well. It's a spherical well.
जब कभी होगा जब रिएक्शन खत्म हो जाएगी.
सिर्फ ये बताओ क्या नहीं समझा. बिल्कुल नहीं कुछ पल्ले पड़ रहा.
पोटेंशियल एनर्जी का रिलेशन ही नहीं समझ आ रहा उसके साथ क्या.
तो बाकी समझ आया कुछ.
बाकी भी समझ
इस तरह लिखने का मतलब है समझ नहीं आया आपको. नहीं सिर्फ
फाइनाइट वेल नहीं होगा, स्फेरिकल होगा, ये फाइनाइट होगा. मतलब उसके लिए फाइनाइट
न्यूक्लियस पे क्या पोटेंशियल एनर्जी होगी. एक स्टूडेंट ने अभी लिख के दिखाया मुझे. किसी और को शाबाश. We've looked at this several times when we discussed the Bohr's model. What's the potential energy of an electron? If I say potential energy Bohr model में क्या थी, आप मुझे फौरन बता देंगे. So this is something you remember as a formula. At y equals 0, we're at the nucleus. The potential energy is minimum, which is minus infinity. As you go further and further away from the nucleus, you're away from the electrostatic field of the nucleus. The potential energy goes to 0. So the potential energy, if I draw a section of the potential energy in one plane, I project it on the plane, this is what it will look like. The x-axis is pointing outwards. So now if I revolve this curve in 3 dimensions, I would get a spherical well. This is like a whirlpool. एक भंवर की तरह का एक है ये स्ट्रक्चर. So at the nucleus, the potential energy is going to minus infinity. It's very small. The electron has fallen into the nucleus. We know that's not allowed by the uncertainty principle, but nevertheless this is what the potential energy is. And when you're further away from the nucleus, That is, when y is very large or when x is very large, then your potential energy is zero, because you are so far off from the nucleus, you're not seeing its field, and the potential energy is taken to be negative, right? Because an electron wants to exist close to the nucleus, because the nucleus is attracting the electron. So when the electron goes closer to the nucleus, its potential energy decreases. It's a favorable situation, because the nucleus is pulling the electron towards it, so its potential energy must go down. If you want to stretch the electron away from the nucleus, electrostatically you have to pump energy into it, so its energy must go up. That's why the potential energy increases as you go further away from the nucleus. In vacuum, when the electron is ionized, it's not seeing it's away from the field of the nucleus, so its potential energy with respect to the nucleus is zero. So this is what this plot really is. It's a well, it's a spiral well, and the bottom is so deep that it's infinity. It's singularity there. And you already know what this potential energy is. It's minus 1 over 4 pi epsilon naught E squared over R. Or what is R? R is simply x squared plus y squared plus z squared under root. So this is the potential energy in the Cartesian frame of reference. I can also write the potential energy in the spherical frame of reference, and that will simply be minus 1 over 4 pi epsilon naught E squared over R. R is the distance of the electron from the nucleus. So this is the potential energy function. Now, does it look easy to deal with the potential energy in the spherical coordinates or the Cartesian coordinates? Of course, in the spherical coordinates. Okay? So the Schrödinger equation, does it depend upon the frame of reference? Any physical law, be it the Newton's law, the Archimedes principle, any law, any principle that you can think of, does it depend upon the observer? The principle doesn't depend. It doesn't depend upon any frame of reference. Even in relativistic frames of reference, Newton's laws of motion hold true. So the Schrödinger equation must hold true in any frame of reference. So if I write the Schrödinger equation in terms of the spherical coordinate systems, I would write minus h bar squared 2m del squared Laplacian operator, the wave function. I'm talking about the time independent part. Now the wave function has to be written in the spherical coordinates, r, theta and phi, instead of x, y and z, plus the potential energy in terms of the spherical coordinates, the energy so everything is clear. This is the Schrödinger equation in the spherical coordinate system. The wave function is now expressed in these spherical coordinates. But what about the Laplacian operator? What about the Laplacian? So the Laplacian has to be defined. The Laplacian, if you know what the Laplacian is in the Cartesian coordinate system, you can derive the Laplacian in the spherical coordinate system. And the temptation is to write it as partial square or partial r squared plus partial square partial theta squared plus partial square partial phi squared. But that's wrong. That's totally wrong. So there is a formula for this which can be derived, which probably some of the interested students will learn about. Let me tell you what the formula is. This is the Laplacian operator in the spherical coordinate system. Of course, you will not have to remember this. But this is what it really is. देखो वॉल्यूम एलिमेंट भी जो था वो डी आर डी थीटा डी फाई नहीं था. वॉल्यूम एलिमेंट के अंदर ये आर स्क्वायर साइन थीटा की एक टर्म भी है साथ, इसे जैकोबियन का एलिमेंट कहते हैं. इसी तरह जो Laplacian ऑपरेटर, दिस इज द करेक्ट फॉर्म ऑफ द Laplacian ऑपरेटर इन द स्फेरिकल कोऑर्डिनेट सिस्टम. In the hydrogen atom, it makes all the more sense to deal with spherical coordinates. Why? Because of the symmetry. Because you change the angle phi. If you change the angle phi of the electron, nothing happens to the electron. It doesn't see any change in its environment. ये बात समझ आई कि if there's a nucleus and an electron outside the nucleus, if you change phi for the electron, if you change the azimuthal angle of the electron, it doesn't see any change in the environment, because this potential energy is spherically symmetric. If you look from the top, you vary the angle phi, the potential energy remains the same. These are circles around an axis, concentric circles. So there is spherical symmetry imposed by the potential energy, because this is a central force. This is a force that is acting on the electron towards the nucleus. It's a central force. This is something you've already studied in mechanics, central forces. So because of the centrality of the force, this problem can be easily treated in the spherical coordinate system. Now what I would like you to do before the next class is, I sent you a document. देखो अब मेरी बात जरा गौर से सुनो. अब वो डॉक्यूमेंट आप में से किसी ने देखा? ठीक है, उससे खौफ ज़्यादा होने की ज़रूरत नहीं है. पहली बात, क्योंकि अब आपने जो ऑर्बिटल्स को स्टडी करना, उनको समझना है कि ऑर्बिटल पी ऑर्बिटल है क्या, डी ऑर्बिटल आखिर में है क्या, उसको समझने के लिए कुछ मेहनत तो करनी पड़ेगी. अब वो मेहनत ये है कि आप उस डेरिवेशन को गो थ्रू करें. मैं आपके साथ करूंगा फ्राइडे को. उस डेरिवेशन के स्टेप्स को हम आहिस्ता आहिस्ता देखेंगे. आई वुड नॉट आस्क एनी क्वेश्चन फ्रॉम यू, बट आई वुड लाइक टू एक्सपोज द डेरिवेशन टू यू, so that you know that the orbitals that we are receiving as an outcome of that derivation, they are making sense. ठीक है? So on Friday we'll go through the derivation, and the goal of Friday's lecture is to understand what an s orbital, why is an s orbital drawn like this, why are the p orbitals drawn like this, and why are the d orbitals drawn like this. And what do these pictures represent? Are they the wave functions or are the probability densities? And how do we get about these? So see you on Friday.